Okay, so a quick recap before we begin. So we were looking at these gradient descent type of algorithms. We started off with the basic or vanilla gradient descent, wherein at each step you take xt plus 1 to be equal to xt minus some step size times the gradient of f evaluated at xt. Right? This is for an unconstrained optimization problem. If you are given a constrained optimization problem, then so far we don't have too many tools at our disposal. But one approach is to do projected gradient descent, wherein you take, say, xt prime to be equal to xt minus delta t times gradient f of xt. So you find xt prime to be equal to xt minus delta t times gradient f of xt, and xt plus 1 is the closest point within the constraint set to xt prime. Right, so this would be projected gradient descent. That's the only approach we know so far, and this argmin, this itself is an optimization problem to solve. All right. But what we know about gradient descent, and also what you can show about projected gradient descent, is that under whatever conditions you have, the running time of the algorithm is order something divided by epsilon, right? Some constant divided by epsilon, or some constant divided by epsilon square, where epsilon is how close the target you want to get to the minimum. Right? So if you want to get epsilon close to the minimum, then you need the number of steps that grows as either order 1 over epsilon or order 1 over epsilon square, depending on what kind of assumptions you make, what you know about the problem itself. All right, and the same thing holds also for projected gradient descent. So, but there's also a corresponding lower bound which says that any algorithm that involves black box access to a first order oracle will require these many number of steps. So the running time is order something divided by square root of epsilon. The question is, can you get close to this? Is there an algorithm that achieves this particular lower bound? And today we'll see an algorithm which actually achieves this particular lower bound. But before that, in the last class, we saw this other problem. We took a detour to look at another constrained optimization problem, wherein you wanted to minimize subject to the constraint that we looked at the following optimization problem. We wanted to minimize some convex function f subject to the constraint that the input must be a valid PMF. All right, so among all valid PMFs on, let's say, n variables, we want to minimize some function f of p. All right, so that's the optimization problem that we were trying to solve, and we were trying to do so using the following kind of iterations, wherein xt plus 1 is obtained by taking the argmin by solving a constrained optimization problem, but with a different function, a much simpler function. So at each step, you are trying to solve a simpler optimization problem for which hopefully you have a closed form solution. All right? And in this particular class of algorithms, we saw that if we took D to be the L2 norm, then this basically reduces to standard gradient descent, nothing else. But on the other hand, if we took this D, the divergence term, to be the KL divergence, then we got a different algorithm which works as follows. So you find the gradient, and then effectively you take e to the power of something times the gradient and then normalize it. Right? So we got this so-called exponential gradient descent towards the end of last class. So the take-home point is that we have this class of algorithms where at each step xt plus 1 is arg min over all x within the constraint set of f of xt plus gradient of f of xt transpose x minus xt plus some regularization term which is going to be a divergence. Right? It has to satisfy some properties, and on the one hand it gives a standard gradient descent, on the other hand we could get this exponential gradient descent. So I'll make a small change to this. So I'll multiply this by some term eta. In other words, eta determines your step size, for example in standard gradient descent. All right, and I hinted that the L2 norm square is one choice of D. Another choice of D was the KL divergence, but in general you could take D to be a Bregman divergence. So D of x comma y could be of the form r of x, some function r of x minus r of y minus the gradient of r of y transpose x minus y. So it's nothing but the difference between r of x and the first order Taylor series approximation of r about y. All right. So let's look at this sort of slightly more generalized setup. So one specific case that we looked at in the previous class was dr to be equal to the KL. So dr was equal to the KL divergence, and we saw that the KL divergence is the Bregman divergence corresponding to the negative entropy. All right. So this is a summary of what we saw in the last class. We'll try to generalize this and see what the corresponding algorithm looks like. Okay, so we'll fix some function r which there's no additional assumptions that we require, but we will henceforth we'll assume that r is convex and what I call closed. Right, we know convexity. I'll say that a function is closed if the epigraph corresponding to R is a closed set. Right, the function R is said to be closed if the epigraph of R is a closed set. So these are the only requirements on R that I have. Okay, and recall that, and dr is the corresponding Bregman divergence. So the iterations that we have, or the algorithm, is you take xt plus 1 to be equal to the arg min over all x in the, let's say, the feasibility set of dr of xt plus some eta times, well, I could take f of xt plus eta times the gradient of x, gradient of at xt times x, but instead it is sufficient to just look at the terms that only involve x, which is just this. Right? This is the class of algorithms that I'm interested in. Right? So this is equal to, now what does this correspond to? What is dr equal to? What is dr of x comma xt? We have a definition, right? What was the definition? R of x minus R of xt minus dot product between gradient R of xt and x minus xt. Right? That's my dr of, that's the Bregman divergence dr of x xt plus eta times gradient f of xt and x. Right? Now, out of these, can I eliminate some terms? So, firstly, the argmin depends only on x. So, I can effectively get these two terms don't really matter. It's just a shift. It's just a constant shift. Right? So, this is equal to the argmin of r of x minus the gradient of r of xt comma x plus eta times the gradient of f of xt comma x, right? Which is the same as gradient r of xt plus eta times gradient f of xt. There should be a minus comma x. Right? Now, assuming that this was an unconstrained optimization problem, what is this equal to? Or what is the solution equal to? Right, let's assume that this particular quantity is, say, Rd. Right? How would you find this argmin? I've told you that R is a convex function. Right? So This term over here is convex. This term is linear in x. So the overall function is convex. So how do you find the minimum? Yeah, you can take the gradient of this whole quantity and set it equal to 0. Right? So what do you get? So gradient r of, so what would the gradient be equal to? So gradient r of x star should be equal to right, or in other words, since xt plus 1 is equal to this arg min, I can say that gradient r of xt plus 1 is equal to gradient r of xt minus eta times the gradient of f of xt. Okay, is this okay so far? Right, so R is basically something that contributes to the regularization term. So we have this. In case F is not all of RD, I'll do a projection step. That is, I'll take xt plus 1. So in this case, let me say wt plus 1 is equal to this particular quantity, and xt plus 1 in x in f, I need some distance. I'm again going to use the Bregman divergence. So you can think of this as, so this is sort of a gradient step. And this is a projection step. Right? At the moment, it's a bit mysterious why I chose this particular Bregman divergence, but it gave me some algorithm. Right? This is an algorithm. And effectively, this algorithm corresponds to solving for this in every step.
What is W here?
So W is some variable that I just introduced.
You have to solve for that, right?
Which one?
For W.
So exactly, you're right. So I have to find W using this particular thing. So Wt plus 1 is going to be, well, this is the gradient of R. So Wt plus 1 is going to be the inverse of gradient R. So here Wt plus 1 inverse of xt minus eta times gradient f of xt. This is assuming that I can actually invert this, right? But this is where properties of convex functions come in. Although I'm not going to prove it, it turns out that if R is closed and convex, then there's an easy way to invert the gradient of R. It turns out this is nothing but the gradient of the conjugate of R. Right? We've seen how to find the conjugate of a particular function, right? So this is right. So there's a deep connection between the conjugate and the inverse of the gradient.
Does this mean that if it's closed and convex, then the gradient of R is unitary? No way.
No.
Gradient of R is
What do you mean by unity? So gradient is a vector, right?
Oh, yeah, it's a vector.
Right, so this is another way where the conjugate helps. So the first connection that we saw where the conjugate came in was in terms of duality, right? So the conjugate, if you're able to evaluate the conjugate, then sometimes you're able to find the dual of a particular optimization problem subject to linear constraints. But here we see that if you're able to compute the conjugate of this particular function R, then you can also find the inverse of the gradient. All right. So that's great. So now I have an algorithm. And this is what is called mirror descent. So basically what do? You start with some initial point x0 that's hopefully close to the minimum. And then you do the following. So recall that I want to first, so these are the two basic steps that I want to do in each case. But I'll sort of split it into some more steps. All right, so this is what I have. I'll first compute this quantity theta t, which is equal to the gradient R of xt and theta t plus 1, or let me call it theta bar t, is going to be equal to theta t minus eta times the gradient f of xt. Right? This is nothing but gradient r of xt minus eta times gradient f of xt. And w t plus 1 is going to be equal to the inverse gradient. So it's conjugate of evaluated at theta bar t. And then if required, you do a projection step, which is xt plus 1 arg min of x in f dr of x wt plus 1. In the case where f is all of Rn, xt plus 1 is simply equal to wt plus 1.
How are you doing the projection?
Which somehow you need a way to do this projection step. So for an unconstrained optimization problem, it's equal to just this. Xt plus 1 is equal to wt plus 1. If you have a constrained problem, then you need some way of computing this particular projection. So I don't get to solve the constrained optimization problem for free. There is some additional work that I have to do.
The only use of R is to reach that lower bound,
As of now, I still have not reached the lower bound.
but it will help.
It will help. So we'll use this to design a different algorithm that allows us to reach that particular lower bound. This is nothing but this particular algorithm over here is nothing but a generalization of the exponential gradient descent that we derived in the last class. That's it. All right. And the reason why this is called mirror descent is because of this mapping from xt to theta t. So we're going from the space xt to the space that is defined by the gradient r, and then coming back. Right? So if I have to draw a picture, then I have this constrained optimization problem. So this is what I call the so-called primal space. This primal and dual that I'm going to talk about has nothing to do with the primal and dual space that are defined by the Lagrange duality. This is a completely different notion of duality. All right? So this is where xt lies. In gradient descent, I would just sort of take a step size in some particular direction to get xt plus 1. Right? But now I do something totally different. There's another space which is called the dual space, where I map xt using the map gradient r, right? The derivative of r. Which one? No, it's gradient r, right? This is my theta t. My theta t is gradient r evaluated at xt. Okay, so I get this theta t, and then I take a step in the direction of gradient f of xt. To get this new point, which is theta t plus 1. Okay, so earlier in standard gradient descent, I would find a direction and take a step in the primal space itself. All right, but now I'm transforming this to a completely different space and then doing one step of gradient descent. And then I'm coming back. To get a new point, xt plus 1. All right. So depending on R, if I didn't have any, say, nice smoothness conditions on R, a small step over here in the dual space could potentially correspond to a huge step in the primal space. Right? In gradient descent, if I fix the step size eta, right, then I would be basically moving eta far away from xt at every step, right, in standard gradient descent. But now I'm taking a small step not here, but in this particular dual space, in the transformed space. So it means that in every step, I could the corresponding step sizes could be really large. They're not all of the same size. All right? So such a map that transforms every point in this primal space to a corresponding dual space is called a mirror map. I mean, there's some more properties that the map should satisfy in order for it to be a mirror map. But if you take R, if you start with a closed convex R, then what you get, you can show is going to be a mirror map.
So how are theta t plus 1 and theta bar of t related?
So theta bar t is equal to theta t minus eta, some constant, times gradient of f of xt.
So like is it the single step which we are taking in the dual space?
Correct.
So then theta plus
Okay. I should have called this theta bar.
Why does this approach even guarantee convergence?
Why does this guarantee convergence? Well, okay, I won't be able to prove this, but you can take a look at the book by Nishit Vishnoy. For the convergence proof. I mean, this idea of mirror descent has broader applications, but it doesn't help us speed convergence. Right? You can show that it converges, and it essentially converges as the same rate as gradient descent did. All right? So, in itself, at this point, we've not got any improvement. Okay?
One more question. If f is equal to r,
If f is equal to r, okay?
then can't you do the entire part in the dual space? You need not remap to the primal space. You could
Well, you typically choose R to be something totally different. All right.
No, you choose R2.
So this function R is chosen totally independent of the problem. Right? You want to minimize f. So if you went back to what we saw in the previous class, right? We took R to correspond to the negative entropy, which gave us dr to be the KL divergence. Right? If I took R to be basically dr to be the squared L2 norm, then I would just get standard gradient descent. Right? So depending on how I choose R, I get a family of mirror descent algorithms. Okay?
Did you make any assumption about F being convex?
So throughout we're assuming that f is convex, because ultimately we want to converge to a local minimum, or we want to solve this constrained optimization problem, which I can only do. All of these guarantees are only for convex f.
Well, so if F is anyways closed and convex,
Okay?
then we're just transforming it into a domain R and then which is also closed and convex and just solve them. I mean, does it really abide by?
As I said, right now we've got no improvement at all right? But in some cases, it does give us an interesting algorithm. We saw that if we take R or dr to be the KL divergence, then I get this different exponential gradient descent. All right? So we came up with gradient descent as one algorithm. Right? We sort of chose it. There was some intuition behind gradient descent, but this is a way of generalizing the gradient descent algorithms. All right? I mean, the whole idea of gradient descent was to, at every step, you try to solve this constrained optimization problem, which was, yeah, you try to solve this particular constrained optimization problem. Right? Now, if I replace this with a different divergence, then I get a different algorithm. All right? And the main point over here is that replacing with this with a different divergence term can effectively guarantee the same rate of convergence. It doesn't give you anything better, but it doesn't give you anything worse. Okay? In terms of the order, I mean, some of the constants could change depending on what R you choose. But at a high level, we have not got any significant improvement yet. Right? Does that make sense? This is just a family of algorithms, nothing more.
So maybe the code for intuition is that if F is a very complicated function, grad F is like hard to calculate. If I just take
It doesn't matter. In all of these algorithms, you have to calculate the gradient of f. You cannot go about without computing the gradient. You need an oracle access to the gradient everywhere, right? So even here, I need to be able to compute gradient f. Right? So the mirror descent algorithm, I have to compute gradient of f, but now I also have to compute gradient of r and gradient of r star. That is why you have to choose r and r star such that you can compute these gradients easily. So you can't just go about choosing a really complicated R. That only makes things worse for you. But if I choose R or dr to be the squared divergence, the squared L2 distance, then I just end up with standard gradient descent. That's the only thing to keep in mind. This is just a generalization of the standard vanilla gradient descent.
could you scroll up?
Yeah. Which part here?
Here.
Huh.
So there you took WT plus 1 is equal to del R inverse.
Correct.
And so you're modifying the step part to del del R star times the gradient of f.
I'm sorry?
If you like take the operator inside, then the
Okay.
gradient of R inverse and gradient of R sort of. So,
This is not a linear operator, right?
so it does not cancel.
No, so this is not equal to xt minus gradient r times that. It's not. Right? So this del r star is not a matrix. It's a function. Could be some complicated looking function. All right?
Del R itself is a vector, right? It's a vector function.
Del r is so del r is a function from Rn to Rn. Right?
Oh, so it's like an operator.
It's an operator. It's a transformation. It's a non-linear transformation. So both del r as well as del r inverse, these are non-linear functions.
So if R is convex, del R star is invertible.
Yeah. So if r is closed and convex, then del r is invertible and it's equal to the gradient of r star.
What is the inverse? Like,
Which
if the gradient inverse of the gradient of x is equal to x, and
gradient inverse of? Correct. So gradient r, so basically for every x, gradient r star of
you can modify the previous step. Right? If
it's
R-
not linear, right? That's the point. So
Oh, it can't be distributed. Okay.
So I can't say that these two terms is equal to del r inverse of this minus eta times the del r of this term. It's not linear. It's not a linear transformation. It's in general going to be a non-linear transformation. All right, so it doesn't distribute. Okay. So next step, I'm just going to present an algorithm. All right. It's not going to be clear as to where this algorithm came from, but then I'll try to give some intuition as to why it works and why it should converge. So this is what is called accelerated gradient descent. And it works as follows. You start with an initial point, let's call it x0. I'm going to have a bunch of different variables. So I'll define z0 to be equal to x0, and I'm going to have another two sets of variables. Right? In every step, I'm not just going to update x, but I'm also going to update z and some other parameters. So I'll define gamma 0 to be equal to 0, lambda 0 to be equal to 1, and gamma 1, gamma 2, gamma 3 are all going to be equal to 0. All right, and for I greater than or equal to 4, gamma I is going to be equal to 2 divided by I. So this is a sequence of numbers, gamma 0, gamma 1, and so on. And I'm going to choose it in this particular way. It's a special way. And at every step, I'm going to do the following. First, I'll compute lambda t which is going to be equal to the product one minus gamma I. Okay, and I'm going to define a yt to be equal to a convex combination of xt and zt. All right. So now I have two quantities zt and xt. I'm going to get xt plus 1 by sort of a standard gradient descent step. In other words, I'm going to run standard gradient descent to get xt plus 1, but I'm going to do mirror descent to get zt plus 1. All right, so zt plus 1 is going to be equal to gradient R inverse of gradient R of zt minus gamma t divided by lambda t All right, so I'm running something like mirror descent on Z. And xt plus 1 is going to be equal to xt minus some constant gamma t So effectively, I'm going to run two different algorithms. I'm going to run a standard gradient descent algorithm, and in parallel, I'm going to run a mirror descent algorithm. And at each stage, I'm going to take a convex combination of the solutions of these two. All right. So in other words, there's one sequence which is x0, x1, x2, and so on. And there is a z0, z1, z2, and so on. So the xi's are going to be produced using gradient descent, and the zi's are going to be produced using mirror descent. But at the end of every step, I'm going to combine these to get y0, y1, y2, and so on. And this convex combination is chosen in a very special way. Yeah?
Decreasing the weight for the product.
We are decreasing the weight for exactly. So as as t becomes larger and larger, I'm giving lesser weight to the mirror descent step, and I'm giving a higher weight to the gradient descent step. Right? Because my gamma t is 2 by I. It grows as 1 over I. So as t becomes larger and larger, the weightage that you give to this becomes smaller and smaller, and the weightage that you give to xt becomes larger and larger. And also, if you look at the step sizes, these step sizes become smaller and smaller as t becomes larger and larger. But it's chosen in a very specific way. I can't choose a different set of step sizes gamma t and end up with the same convergence result. And the main result here is that to get epsilon close to the minimum, it is sufficient to run this algorithm for square root of LD square divided by epsilon steps. So now we get a running time of order 1 over square root of epsilon compared to the order 1 over epsilon and 1 over epsilon square that we had previously. All right. So in itself, mirror descent was bad. In itself, gradient descent was bad. But by taking a combination of these two, I magically get a much faster algorithm. Right? So this is a very general idea that's used in many different applications to come up with algorithms that are better than gradient descent. This sort of an acceleration mechanism, wherein you take a convex combination of the gradient descent and something else, which is typically mirror descent.
Why is it becoming faster?
There's no direct intuition behind why it is becoming faster. You just have to go through the proof. And it's not an easy proof. There are a whole bunch of different steps that are involved. But I'll try to give a very high level of overview of what is going on. All right.
You can in fact say that T is big theta of epsilon, big theta of that.
I'm sorry?
Instead of big O,
Correct.
it's also lower bounded, so it's exactly that order.
Agreed. For specific subclasses of functions, it could be even faster. Right? Because that lower bound was for a very general class, for the worst case f. That is the minimum number of steps that you require. For certain functions, it could converge even faster. Right. So the idea behind showing that this is optimal, or the main idea behind accelerated gradient descent is again, you try to minimize a sequence of functions that approximates f better and better as you go along. Right? So if you recall in say mirror descent or even standard gradient descent, we were trying to solve this approximate minimization, right? Yeah. So you are trying. What were you doing at each step? You were approximating f of x by something that is linear plus a regularization term. That was the high-level idea behind this class of gradient descent algorithms. Right? But at each stage, you don't have a better approximation of f of x or f of xt. Here the idea is, okay, you don't universally approximate f better at every step, but you try to approximate f at xt better and better as you go along. I'll try to make that more formal. So in particular, suppose that we are able to find a sequence of functions, let's say phi 0, phi 1, phi 2, and so on. At every step, at the tth step, I try to minimize the function phi t. Okay? So you minimize phi t at each step. And this phi t is chosen to satisfy certain properties. The first property that it has to satisfy is that phi t should be sort of an I want tight upper and lower bounds on phi t in terms of f. So I want phi t to approximate f better and better as we go along. So phi t of x should be less than or equal to 1 minus lambda t times f of x plus lambda t L by 2 sigma times phi 0 of x. Let's ignore this quantity over here. It's some constant. But phi t of x is basically a convex combination of f of xt and phi 0 of f of x and phi 0 of x. It can be upper bounded by this convex combination. And as t becomes larger, I want lambda t to become smaller and smaller. So if lambda t is small, then phi t of x is almost upper bounded by f of x for all x. Okay, and I also want a good enough lower bound, which is that at every step of the algorithm, I'm not just going to update phi, but also I'm going to update xt, right? I'm going to get an xt at every step. I want f of xt to be a lower bound on phi t of x for all x. I'm sorry? How do I choose phi naught of x? I will choose phi 0 of x to be exactly equal to f of x naught, some constant, times f of x naught, or I should say f of x naught plus some constant times dr of x naught. Which one? This is the only thing that works. Okay. Again, it's difficult to give intuition as to how you come up with this particular algorithm. That's very hard. But all I can say is give you some intuition for why it works. All right. It is, in a sense, it's not intuitive as to why this should work beforehand. But then using a few steps, I can show that yes, it achieves this particular convergence result, this particular rate of convergence.
This lowest convergence is achieved by only this general category of function.
Not necessary. This is an algorithm that achieves this rate of convergence.
So there could be ones of slightly different form.
There could be a totally different algorithm that achieves the same rate of convergence. All right. But this is a general approach that seems to work very, very well in many different classes of problems.
So how are you selecting phi and p?
Which one? So this is how I'm doing it. Of course. How do I get phi t? Effectively, it comes from the algorithm. But suppose I am able to do so. Okay, suppose I am able to construct phi 0, phi 1 and so on such that these two properties are satisfied. Okay, if I am able to come up with such a sequence, then I claim that I can achieve that rate of convergence that I promised. The second claim is that this particular algorithm, accelerated gradient descent, does precisely that. That second part I'm not going to be able to prove because that it's fairly involved, showing that this particular algorithm, or in other words, how you come up with the sequence of functions phi, that requires a little more work. All right. In fact, I'll sort of give you something like an explicit form of how you choose phi t, but how I came up with that particular choice is not going to be clear. And why it satisfies these properties, that I'm not going to prove. All right. So I can give you that directly right now. So I'm going to choose another set of functions. So I'll define LT of x to be equal to f of yt. Again, this comes from the accelerated gradient descent algorithm plus okay, and phi t plus 1 is just going to be a convex combination of phi t and LT. Okay. So this is how I choose phi t. The claim is that this choice of phi t satisfies properties 1 and 2, which I will not prove.
When was this algorithm discovered?
Fairly recently. Well, when I say fairly recently, a couple of decades ago. But that is still relatively recent. All right. And claim 2. then we can achieve T to be order LD square divided by epsilon. So I will prove claim 2 in the next class, but now we are going to have a quiz. Any questions before that?